the last video, we introduced circuits, a new framework for providing low-level algorithmic explanations of language model behavior. In this video, we're going to learn how to find circuits. To recap, we're studying the greater than task, which gives a language model inputs like the war lasted from the year 1741 to the year 17... We want to know, how does our model assign high probability to valid continuations, like 42 or 63? Fundamentally, a circuit needs to tell us which model components are important for this task. We test a circuit's correctness by knocking out or ablating edges outside the circuit and seeing if the model's performance changes. So we need to find out which components can and cannot be ablated without hurting model performance. How can we ablate components? We could ablate a component by changing its output to 0, leaving it unable to perform its job. In this video, however, we'll do something even stronger. We'll replace component outputs with outputs from other examples. Specifically, we create a corrupted example. The war lasted from the year 1701 to the year 17... which elicits very different answers, like 02 or 03, compared to the previous example. Thus, when judged by our metric, that is, the probability assigned to valid years, greater than 41, minus that assigned to invalid years, the model performs much worse on this example. Now, given this example, we perform this replacement, called activation patching, by first running the model on the corrupted input and saving its output activations. We then run it again on the normal input, but replace the output activations of the components we want to test with corrupted activations. Now, if the target component was important, this should push the model towards poor performance. Thus, if model performance changes, the targeted component was important, otherwise it wasn't. Note that in the prior example, we performed activation patching on an entire component, a multi-layer perceptron, or an MLP. But in our circuit diagrams, we claim to show the edges, or the relationships between components, that matter. So how can we test that? Well, actually, we can test that in the same way as with components. We can ablate an edge and see how model performance changes. If it changes, the edge is important. Otherwise, it can safely be discarded. Now, we know how to do activation patching on individual nodes and edges, but how can we find a whole circuit? Well, we can actually just iteratively apply activation patching. We'll test every edge, starting from those going into the logits, to see if it is important. In the first step, we see that some of the edges going into the logits, those marked in blue, are important, and others, marked in red, are not. We then proceed to the edges going into MLP11, once again identifying edges that are important and not important, as determined by activation patching. Since attention layer 11 has no outgoing edges, we can safely skip over it and look at the edges going into MLP10. This continues until we've tested all edges. Those that remain form our circuit. Now note that this is a process that scales poorly. Testing an edge requires a forward pass, and larger models have more edges and more expensive forward passes. These days, circuit finding is typically done using gradient-based approximations, which require only a fixed number of forward passes. Now we know how to find the structure of a circuit. But how can we know what each of its components does, as indicated by the labels on the right? Today, we'll answer that question with the logit lens, a technique that allows us to view model activations in interpretable vocabulary space. So during a typical forward pass, the output of the model's final layer is multiplied by the unembedding matrix. This yields a vector of scores, or logits, one for each potential output word, indicating how likely that word is. But the output of the model's final layer is just the sum of each preceding component's outputs, In fact, this is true of all model layers. This means that we can also multiply other model activations by this unembedding matrix to understand them in vocabulary space. For example, if we multiply an earlier layer's output by this matrix, we can do early decoding, finding out the model's intermediate predictions. On the other hand, if we multiply the output of an attention head by this matrix, we can see how it contributed to model predictions. Doing this is called the logit lens. We can apply the logit lens to our question of interest too. Consider applying the logit lens to one of the attention heads that we identified as important, say A7.H10. When we convert the output of this head into vocabulary space, we can see which years it upweights more highly. The spike at the year 41 indicates that this head made it more likely for the model to output 41. Although this isn't actually the correct answer, it shows that the head did identify the correct start year. Applying the logit lens to a multi-layer perceptron, say M10, shows that M10 upweights the correct answers. All of the years past 41 have a notably higher logit lens value than those that came before, and there's a sharp cutoff between valid and invalid years. In this way, we can determine what role each component plays. Now we've learned to characterize circuit structure and semantics. To do the former, we've applied activation patching to find which model components and edges matter. To do the latter, we've applied the logit lens to transform component activations into vocabulary space. That said, there's plenty more in the world of circuits and interpretability beyond this. Circuit analysis is still a very young technique, and there's still much more work to be done.